Hi everybody. First of all, I'm happy to be here to present the telescope in this conference in honor of Massimo Capaccioni, because okay, you all know which was his role in this project, and usually he presents this project in this room. So it's really an honor for me. These two pictures represent two devices for astronomy that must be studied together, in my opinion. Thank you. Okay. Is it a very small telescope? Probably not, because it's located here in the Isoparanal Observatory. It's that we call also here in Napoli Paranalcatraz, because in Neapolitan language it means something like, it seems like Alcatraz. It is the most productive astronomical observatory in the world, so we're very proud to be here with our instrument, and that is an enough realization. So, in other words, this is the slide showing the instruments in Paranal, instruments and telescopes. Some of them have been realized directly by ISO. Many others have been realized by external consortia with the ISO collaboration together. In many cases, there has been the collaboration of Italian institutes. And talking about telescopes, most of them have been realized directly by ISO, for UTs and for auxiliary telescopes. And then there are two external contributions by UK and Italy, that are VISTA and VST, which are by far the two largest external contributions, because they are really large in terms of cost and budget. And this is the only instrument with Italian leadership in what is considered the best observatory worldwide, the most productive at least. A bit of history of the project. It was an idea of Massimo. In 1998, a memorandum of understanding was signed between the Astronomical Observatory of Capelmonte, just a few years before the creation of the National Institute for Astrophysics. And according to this memorandum of understanding, the Observatory of Capodimonte and then INAF was committed to produce the telescope. ISO had to provide the enclosure, and the American consortium composed by Netherlands, Germany, Italy, and ISO had to provide the camera. And the idea was that the operation and maintenance was sustained by ISO, therefore we did not pay a fee, an annual fee for this telescope. Also, we can say that this is the first active optics telescopes totally designed in Italy by scratch, because the only previous experience was the TNG, that was partially a replica in the optomechanical design of the entity. So in that case, it was hard in any case, but for us it has been harder and harder. The Omega Cam camera is an impressive array of 32 scientific grade CCDs, with other 4 CCDs on the outer edge. They are provided by Conrad Koike and his team, and the other 4 CCDs are used for auto-guiding and image analysis with the curvature sensor. The pixel scale is 0.21 second per pixel, and probably you already know these things. The optical design, okay, these slides are not visible today. So if you can fix it, otherwise. Anyway, I will continue to talk about it. It's not a pure Chicletienne, because there is a corrector to get a wide field of view and to get a corrected field of 1 degree by 1 degree. So the primary mirror is convex, it is concave, the secondary mirror is convex. We have also an active optics system based on an M1 support system with 8 4-axis supports and 1 active, 3 are cones, and we modify the shape of the primary mirror this way. Also, we can modify the position of the secondary mirror using an X-cone, which can move the secondary mirror in 5 degrees of freedom. And then we have the 3 lenses of the corrector, 2 arrows in the telescope and 1 in the camera. These are the mirrors, the M1, 2.6 meters, the M2 on top of the telescope, 0.9 meters. This is one of the length corrector, and you can see also the precision tools that we use for installation on the right side. It's a 2.6 heads length. A step back, we had some years of integration in Italy, in a town, in a small town at 40 kilometers from here. At the end of this period, in 2006, the telescope mount and tracking system were fully ready. They were ready. We had still something to do. In fact, we were supported by some external companies. We went to ABS premises in northern Italy to work on the exoport, and also at Tonelleri in Verona, also in northern Italy, to complete work on the primary mirror super system. At the end of this period, it was 2009, we were quite satisfied. Here you can see Raffaele Tonelleri and Massimo Proccioli posing for the picture just 3 days before the shipment. Also, Applied Optics used our picture as a front cover. But we had to ship, and you know that shipments were not very lucky in the history of the project. We had already some problems some years before, in 2002, shipping the M1 mirror. Probably the container vessel was like this, and the result was this one. The mirror was destroyed. We have one piece of glass in the office of Massimo that you can admire 30 meters from here.
And euros.
Then in 2009, we repeated the same error because we had a container vessel like this for the M1 cell, and the result was this: all the devices were completely covered by rust, and so we wasted a lot of time and a lot of money. It was a disaster, and we still have something with us. This is one of motors, for example, but I have many of them. And okay, there were also some tanks because was everywhere. But as a true PI, never give it up. We recovered the situation, and of course, using a lot of time. And the cell was shipped back with 1 year of work more. It was installed in the telescope, and we arrived the November 30th, 4 years ago. So exactly 4 years ago. By the way, November 30th is my birthday next Sunday, so please remember. And it was a technical test flight using a reflex camera, Omega Canon, and Roberto Ragazzoni was there to lead the group of this technical first flight. It was the result was okay, they were all happy, and Roberto had to call Massimo. There was a phone call during the night. These slides were kindly provided by Roberto. Roberto was in Chile, Massimo was in Napoli, and okay, it was during the night. So the conversation is reported integrally here, and Roberto said, Massimo, this is the technical first flight, everything okay. We had less than 12 seconds, we were close to Christmas, as you can see, and the answer was this one. So. I kiss you in the mouth, so coming out after 70 years. Some words about commissioning. Commissioning results, I will go very quickly. These are results for quantity modeling. If we do a quantity model, it is done automatically in less than 1 hour. We can do it. The results are comparable with the UTs, so we have more or less a fit around 1 second. Of course, I'm showing you the best result that we have ever obtained, that is 0.8. But for the thermal control, we also had results within the specification. We have few hundreds of seconds or error for each axis, also in windy nights. When I performed this test, I was stopped because they called me, telling me that we had overcome the environmental limit of Paranal and we had to close. So we were at around 18 meters per second as a wind speed. The auto guiding also performs very well. We have indeed 2 auto guiding systems, one in the telescope and the one in the camera. We use for operational reasons. They both perform in the same way, but we use the the camera system because we have less overhead this way. This is our system. Okay, we'll not go into details. Here you can see the M1 system, sorry, the M1 system, the hexagon, the M2, and our Shakafman, that is the wavefront sensor embedded in the telescope. Everything is operational, but we use normally the camera system because it has innovative parts and it is much better because we don't have to wait for the probe coming in and out. This is developed by Conrad Koiken of the American group PI, and is based on the analysis of donuts of intra and extra oval images. Some words on the alignment, just to let you know that it is much more difficult for a telescope like this than a conventional telescope. Here you just look at the situation before and after the last step of our alignment. You can see that at the center of the field we have already good image qualities. This is 0.5 at second, but this is very bad in one side, on one side of the CCD of the mosaic. It goes up to 1.5. But with a telescope which has a field like this, like conventional telescopes, you would have no problems. In our case, it was much more important to get a perfect alignment. If we are not perfectly aligned, it is perfectly visible in the images. So in the end, we arrived after this period to the first light with Omega Cam. We were moderately satisfied, as you can see. And okay, we can see also that we got to a PST 2.0 in a certain way because we had the first years of the project in which we were a bit slow, then we did a big acceleration, and these two telescopes that you see are the same, but indeed they are different in many details. The sharing of work, as you can see from the slide, we did internally a lot of work within INAF. There were also, of course, some industries in the group, especially EIE for the enclosure and the contract divisor, especially Tonelleri for the M1 system and BTS for the M2 system, and also others with small involvements. But anyway, this way it was harder and cheaper, of course. ISO has given fundamental help in all phases of the project, but we have to thank them for the support. We got the preliminary acceptance in Chile exactly 3 years ago, and the final acceptance last month. But since October 15, 2011, PST is fully available for science every night. So all commissionings are ended, telescope and camera, and so 365 nights per year the telescope is available for science. Now with this slide, I just want to compare the time with the time for the realization of the telescope, from proposal to a fully operational telescope. That means, according to my definition, it's telescope fully operative, all commissionings, all ended. We took 14 years from 1997 to 2011, and here you can see some other projects that are medium-sized telescope based on active optics. So you can see that, okay, of course, you can take less, but if you propose now a new telescope based on active optics, you will have probably something to do for the next 10 years at least. And also, I think that in our case, we have to consider that a couple of years have been lost for shipping disasters, so I think that more or less, and in the end, we are aligned with times that other teams have needed. The agreement between ISO and INAF for the operation of the telescope, the GTO and the loan of the telescope is different. Yes, I will go faster. We are still in group. The telescope has been finally accepted, but it is still property of INAF, so we are still in group for upgrade, maintenance, and so on. The observing time is shared in this way. The INAF GTO is going from 10 to 20% along the years, and of course, most of the time is for the public service. The image quality is the most important magnitude function for this telescope. It is quite good. We go down to 0.5 at second to hit at maximum images regularly. And probably our lower limit is this 0.45. So maybe we can do also slightly better, but it's not so bad. Also, again, look to kids data or Atlas data. Yesterday, Tom Shanks did a wonderful presentation on all of these. I have just looked in Google for histograms on this data. So if you see the bar of 1 second, you see that for kids, for example, we are most of the time. Sorry. For kids, we are most of the time on the left side of this bar. And the same is for Atlas, and we can also have a look to pastors, for example. In this case, we see that for most of the observation, we are on the right side of this bar. And this is the same for the dark energy survey camera, for the slow digital sky survey. This, I have not found histograms, but from this paper, I would say they are also in a very good shape, and more or less they have very good, the same very good performance. Talking about this efficiency, this is a point where we can improve. Anyway, the science time that is currently the time that is currently used for science for this is 37%. We are trying to work together with ISO with an effort to do it better. Anyway, just to make an example, pastors is at 35%. So these are not numbers that are totally out of the world. We are more or less aligned with other telescopes in our team, but we know that we have to improve a bit here. Another future improvement is the possibility to do the active optics with the wavefront sensing without the wavefront sensor, just using the images and analyzing the images, because you know that in such a large field of view, the signature of optical defects is very clear. But this, for example, in this picture, you see the effect of the misalignment between the M1 and M2. And the pattern is very clear. The problem is, of course, to distinguish between the different error sources, especially when they are small, because when they are very high, it is very easy. We are working on that, and we are trying in a long time scale to do this kind of work. And in the end, just let me thank a lot of people. I have put many pictures, but they are not enough. Especially I would thank Gabriele Umbiago, who is following us on streaming. So ciao Gabriele. And okay, the very end, we can well say, I think that thanks to this man, we have changed the landscape of astronomy in Naples. So è qui il massimo.
In fact, let me add to this. Apart from all the fantastic science that is going to come out of this, I think what is impressive, what we all know and what you've described, is the setbacks that the project had. How much perseverance and courage Massimo Capaccioli and his team had to push this through. I think this is a lesson to everyone to insist, and even with setbacks to get on. And I think this is really a wonderful example. I mean, are still competitive if you just have the courage to go on.
This is the visionary.
This is incredible. Do we want to have some comments and questions?
I was curious to know why the second ship, why the vessel was contributed.
I don't know. Of course, that is a picture that I've taken from Google.
Okay. But it was underwater.
Well, indeed, we don't know what has happened. What we know is that the old mirror cell and also the M1 line were totally invaded by water. And really, we have seen with our eyes all the water that was inside the boxes. It was something incredible.
I've got maybe a bit of a cheeky question in this respect, but you had to redo, certainly after the second problem when things came back with the rust, did you, I mean, were you able to do some improvements? Were there things that you had thought about more in the meantime, or do you think there's something that had gone better because of those setbacks, or did you just reproduce exactly what you had before?
Well, we were in hurry because we could not redesign things. Of course, doing this the second time, I would do different things in some cases. But in that case, we could not do experiments. We had another year of work because we had to redo all the devices and to test them again and to qualify them again. We were very worried because we have one system, because all these supports are not accessible. So they are not accessible from the top, they're not accessible from the bottom, and so they must be absolutely reliable. And so we decided to change all the moving parts, all the motors. And we had also some surprises because, for example, the load cells were different. We bought some load cells that were supposed to be identical, but they were not. So we had to rewrite the firmware. So we had many problems with this.
What is the contribution to the seeing from the optics? Because it was specified, wasn't it, 0.4, 0.43 arc seconds, and you're getting 0.5 arc second overall seeing. So it must be smaller, surely, than 0.43 from the optics in the R band.
Yeah, I think that in principle you should be able to go down to 0.3, 0.35 in exceptional seeing condition. I think we should. We have never been able to do it, and so I think there is still a small room for improvement. But what can be the reasons? They can be or high order modes, aberration modes that we do not correct, or maybe that we never get perfect focus and perfect correction and the perfect alignment, because as you have seen, it is very sensitive to alignment, to misalignment of the results. So one thing that you are doing is to try to get a system to align better online the text scope in order to reduce astigmatism from misalignment. That is a serious issue in this case. And there are two parallel efforts. One is the one that I've shown you before, and also Konrad Koigen is trying to improve his algorithm using GONS.
Okay, excellent. Let's thank all the speakers for this session. We had a cancellation, so there's no rush. We can have the full half hour for our coffee break. So let's reconvene at 11:35. Okay, 11:35. We get back.
Yeah, she knows. History. Yeah, I think she probably looks like it's one of the okay, thank you very much. L'unica cosa volevo